Hey, this is Charlie Horvath, a volunteer with the Charlotte Fablab. And after talking to Tom Dubik, I wanted to offer basically some additional context, or maybe a volunteer recitation on CNC and how it fits into the industrial picture. Because I had the great fortune of working with a great company, Shunk, for 3 years to start my career as a mechanical engineer within this industry, and there's a lot of cool stuff I want to show you, so let's get right into it. So just a quick overview of what we'll be looking at, kind of why all this stuff matters, some important concepts, the current state of the industry and markets, and then some automation and kind of cutting edge technology. So I just want to clarify one quick thing, because I think it's often misunderstood. And my dad keeps asking me, what does CNC stand for? Technically, it stands for computer numerically controlled. Now, that doesn't really tell you what we're talking about. That could mean a lot of things. Technically, all of these machines, ShopBot, 3D printers, robots, could technically be considered computer numerically controlled. Most of them run on G code or similar code. So that being said, when we say CNC, more often than not, we're talking about subtractive manufacturing, milling machines, turning machines, basically cutting away material to form a part. So when we're talking about the CNC industry, I'm going to mainly be able to tell you about metal cutting. That's the industry I was in, which is a huge industry. There's some overlap there with plastics and ceramics, and but what I won't be as much your guy when it comes to wood cutting. I know we've been mostly working on shop bots and wood cutting. Somebody else could tell you about that industry. I don't know much about it. I don't know how big it is, but I'm sure it's a booming industry as well. But metal cutting, it shares many concepts. So it's not a huge distinction. It's just slightly different machines. But you've got turning here, so basically like a lathe. You got milling. So this is cool. This is actually like what we call multitasking or a mill turn machine. So it's got all of this capability under one roof. So right now you see pocket milling, probably a stainless steel part here we're seeing. And then it's going to get into some 2.5D milling, and then come back and smooth all of that over with some 3D milling. And so here you see this is actually a 5-axis machine. We'll get into everything we just saw, but one thing I want to point out is even at this level, this is pretty advanced, you still see toe clamps. So some things don't change, much like what we used on the ShopBot. So why does this industry matter? It's in a lot more products than you might realize. So on the left we got an engine block, and implants are machined often out of solid titanium. Aerospace, so many different parts. Basically anything that requires moving parts needs to be precise. That usually is CNC machined, or anything that requires precision. Other technologies are better when you need just like a simple flange or something that's not necessarily needing to be smooth or precise. But this is where CNC shines. And this was one thing I'll get into a little bit about what I was doing, but this is one thing that was cool about my job is that every day was something different. Like, oh, here's a lawnmower blade today, and then a kneecap tomorrow. It kept it pretty fresh. So an important concept that I want to make sure is clear is basically the number of axes of a machine is really important to driving what that machine is capable of. So in the middle we got 3-axis. Basically what we've been working on is the ShopBot, so a 3-axis mill. And I think most of us kept it to basically profiling and 2D milling. Basically just cutting out 2D shapes, which has a lot of overlap with what you could call 2.5D milling. Basically once you start adding pockets and different levels, you see like that topographical map. And then what the ShopBots are capable of, but I don't think any of us have taken advantage of this week, is actually 3D milling. So that's when you take, you would mill that topographical map first with 2.5D passes and a flat end mill. Then you would come back with the ball nose and smooth it over, much like we just saw with that that rim being machined. Backing up a bit, you've got 2-axis, which is more often called lathe work or turning. And so this is slightly different than a mill. Instead of having a spinning tool in a stationary part, you have a spinning part in a stationary tool. And it's really good for building symmetric round parts. Similar concepts, even though it's different. Now moving up in the mill world, you've got machines that add a 4th axis. So what this allows you to do is gain better access to the part, and adding that 4th axis can really enable a lot of flexibility. So like for instance, if you were trying to build this valve block down here out of say brass or something, so it's got features on 3 or 4 sides. So imagine being able to hit all 3 of these sides, 1, 2, 3, in one fixturing setup. Rather than, say, if you were on a 3-axis mill, you might have to fixture the part 3 different times to get all those features. So it's all about reducing the number of setups, because I'm sure you guys have noticed how long it takes to set up a job or a part on the ShopBot. So in industry, it's all about reducing the number of operations and reducing the number of setups. So moving up, in 4th axis, I'm told, which came about, I think, in like the 70s and the 80s. And you even, I think our lab even has a 4th axis attachment for like the laser cutter. It definitely opens up capabilities. Moving up, you've got 5-axis, which is really, it's been around for some time now, but it's really finally becoming affordable, and the industry is really making a lot of use of it. So just like that 4th axis adds access to the part, now you've got the whole table. Not only can the part spin, but the whole table can turn. So you can get at basically 5 sides of a part. So much like 2.5D versus 3D, we can split this into 3+2 versus true 5-axis. A lot of people in industry are using 5-axis just for part access, because you can get at 5 sides. And then in rare cases, if you need a really complex shape, the machine is capable of doing simultaneous cuts in that way. And then what we saw earlier, moving up from there, basically machines, they just keep adding axes. I mean, I've seen a 9-11 axis machine. It gets crazy. But basically, you get to the point where you've got turning and milling in under one roof, and you've got very few limitations on what kind of geometries you can create. And all in one setup, or even sometimes 2 setups under one roof. Beyond that, how do we get more complex geometry? Because even in this case, you're still limited by subtractive manufacturing. You still need to be able to get that tool towards the feature, and you can't create like internal lattice structures or internal structures as easily. So that's where additive manufacturing is coming onto the scene. This is definitely on the cutting edge side, but you've got metal additive technologies. Basically, in some cases, it's as simple as like a 3-axis weld torch.
and in other cases it's like a powder stream that's getting sintered, and we'll see a little bit more of that. But then what's cool is under the same roof, under the same machine, they have additive and subtractive tools that can swap back and forth. And we'll see in a bit why this is so useful. But I talked to a guy at a trade show here, looking at some of these parts, and I asked, like, one, how much do these machines cost, and like how many are out there, and you're basically starting at $1 million machine at this point, whereas like maybe these mill turns are like 500,000. You could probably get a 5-axis machine for 200,000. A good 4-axis is around the same price. 3-axis mills maybe starting at 50,000. A lathe probably in that same ballpark. So you're at $1 million here with these hybrid additive subtractive machines just starting. And he said maybe at that point, that was like 2018, there were like 17 in service from their brand. A few different brands carry these types of machines, but it drives a good point, and which is that, and I think this is often missed, you're not, with each of these step ups in technology, you're gaining capability, and the design engineers are less handcuffed than ever before. But with capability and complexity, there's increased cost. So it's not necessarily that someday everything is going to be made with hybrid additive subtractive mill turn machines, because the cost is insane. So it's always about deciding the right technology for the part you're trying to make. And for instance, if you want to copy your house key, like the key you use to get into your house, you go to Lowe's and there's a little key cutter machine, which essentially is like a 2 or 3-axis mill. That does the job great. There's no need to add any additional complexity. And I would bet $1 million. I am a betting man, and I would bet $1 million that we'll never be using additive subtractive technology to create house keys, because there's just the risk, the cost trade-off just it'll never add up. So these machines, as they get more complex, they're being used to create really high value parts, $100,000 parts, etc. So jumping back a bit to the market as a whole, so it's got a pretty even breakdown around the world right now, or I guess circa 2016. And one thing that surprised me, I worked for a German company. Europe's got a pretty rich history with metal cutting and the CNC world, with like Swiss watchmaking and automotive. And the two trends we're seeing now is that China's, as always, the rising giant, and they are just the last few years, especially before COVID, we're just absolutely booming, always growing in their manufacturing. And then you've got kind of this wave of bring manufacturing back to the United States. So you've got a growing market there as well. And had it not been for COVID, it was a steady increase. Our company was steadily increasing revenues. The whole industry, more machines being sold, etc. COVID was a dip, but I anticipate this being a growing market for the foreseeable future. And industries we served, like I said, a really wide range, but some notable ones: automotive, of course, aerospace, medical, weapons defense manufacturing, and then one thing that's important to note is that a lot of our customers were suppliers. So shops that specialized in CNC, sometimes called job shops. So while huge brands like Honeywell and GE have a large need for precision metal parts. Oftentimes that work gets farmed out to suppliers. That's a generalization, not always the case, but a lot of times CNC takes so much effort that it makes sense to have shops that dedicate themselves to it rather than trying to bring that all in-house. So more generally looking at the job market, these numbers aren't specific to CNC, but you've got this perhaps oversupply of high skill workers. That's something I noticed, is that, I've been hearing my whole life that there's this lack of engineers, lack of enough technical people. Well, I'm here to tell you there's a lot of mechanical engineers graduating every year. And perhaps even soon we'll have a true oversupply of certain types of engineering. And this topic requires much more time to discuss. I'm happy to do it. But so we've got plenty of engineers, but not necessarily enough what you might call middle skill jobs. And in this case, like a machinist or a tradesman or even just a machine operator would probably fall under that middle skill section. And there is a huge lack of machinists specifically. You've got basically tons of them retiring. Many baby boomers have made great careers out of this world, and they're retiring, and with them is a lot of knowledge retiring. And unfortunately, the United States doesn't have a good trade school backbone, or they have one, but it's growing, and a lot of that knowledge is being lost. So we do need people flooding into this world, but for the time being, what do you do if you have too many engineers and not enough people to run the machines? Well, you automate. One reason we do that is that setting up an automation line is a suitable job for engineers. It takes a lot of upfront effort, and then once it's running, you basically just need a security guard to watch it. So a little bit about automation, industrial automation, that is. This is what you could maybe call the old way for metal cutting, and this is a pretty crude example, but something like you would see on How It's Made, where you've got a metal part being passed down the transfer line, and basically at each stage it's getting maybe 1-2 features machined in, and then it's getting pushed along. So for certain types of products, I'm sure this has been a great way to produce, and obviously this is like I said, crude, but it gets way more high production than this. But imagine, one of these machines or just fixtures or setups needs to be serviced. Well, all of a sudden you're shutting down the entire line. Or imagine you want to change one feature on that product you're offering. Well, do you need new tool? Do you need new machine? Do you need to change the floor plan of your shop to change this line? Sounds like a nightmare to me. So, where the industry has moved is towards CNC machines, where all those different machining processes can happen under one roof or within one enclosure, so to speak. So other products still make sense to make that way. Paper production, you need a continuous line, basically, like an extrusion process of just like miles and miles of paper are coming out of that plant at any given time. But for metal cutting, it's making less sense to have that continuous line and move to things more like this. This we call machine tending here, where you put a 5 or a 6-axis robot out front of a machine that does the part loading. So this is an example we had at Shunk where I worked, and so it's cool. You started with these blanks on the left, so sometimes called billet, just a solid hunk of metal. The robot loaded it into the machine, and it came out looking like this on the right. Nearly a completely machined product for us. And that is all within one setup, like a 13-minute runtime to machine that. And the robot loads it and unloads it for you. And this can run overnight. So you set up a job to make 60 of them, and you come back in the morning and you've got 60 parts like on the right. Here's like a pretty advanced version of that. So whereas that job, you basically had automated part loading. This is an advanced cell where not only can the robot change out different parts, it can actually change out, collets and tools and switch between different jobs and allow you to say, let's say when I go home at night, I want 50 of this part in the morning and I want 30 of this part in the morning. Well, now the robot's able to actually handle multiple jobs and automatically switch between them. So a much more advanced setup here, with much more engineering work going in on the front end, but you're left with a much more useful robot cell at the end of the day. So this is kind of like the cutting edge automation of maybe the last 10 years, but even more so where the industry's heading, or what's a new capability is kind of flexible automation. So those robots we've been seeing, you'll notice they were fenced in. That robot would hit you with a haymaker and not think twice about it. The first robot, it didn't look so fenced in, but actually what was there was a laser gate. So not quite pictured, but if I had taken 2 steps forward, this robot I would trip a laser, kind of like your garage door opener, and this robot would automatically shut off, because it can and will hurt you. So what the industry's moving towards are called, sometimes called cobots. So robots built for human collaboration. So when this robot, it has collision detection. So if it accidentally knocked into you or anything else, it would shut itself off and not be able to hurt you, theoretically. So you can see like this guy can work in the vicinity of that thing safely. And then the other key distinction that my company always harped on is not only are these things safe to work around, but they're much easier to program. So this guy is actually, this is the simplest way to program is he's put it in a teach mode, and you'll notice he's pushing it around by hand. So that robot is going to remember the movements he just pushed around, and it can repeat those movements. Also, if you need to use the control software, it's very intuitive, much more so than those industrial robots that we saw in the past 2 examples. Those things, I hear you borderline need a master's degree to program, but this is much simpler. And the key capability that this opens up is that you can automate small part runs. So let's say you needed to run 500 of a part, which is a pretty common need. In those previous examples, by the time you got setting up that robot and that fence and everything, you could have probably run 1,000 parts just having somebody hand load them. But here, this opens up flexible automation and the ability to automate short runs, which is in a way sort of the holy grail of automation, flexible automation. It's almost an oxymoron, but we're getting there. So yeah, these are so easy to program that let's see, they were able to teach a fool like me to do it. So yeah, in about half a morning, a colleague was able to teach me not completely how to control this thing, but enough to feel comfortable where I could fiddle around with it and not break anything. So amazingly easy to program, fun to work with, easier to program than a CNC machine, but they really complement each other. So again, I got to work for this company Schunk. It's a German brand. great company, really good people, and they have 4 product areas. I was focused on the stationary work holding side, which is another word for fixturing on mills, and that was kind of intimately related to the robot side, because anytime you're trying to automate, you have a robot that needs to pass that material off to the machine, and so you'd have an automated piece of fixturing as well. So our biggest product group is gripping systems, or basically robot hands. So there was always that handoff that was important for automation. So we had the cool thing about Shunk is that anything they built, they were trying to be the best product in the market. So we had some really cool toys to play with. For instance, this piece you see on the table right there was one of our flagship fixturing products. So you may have noticed that it takes a while to add anything to the ShopBot table, to fixture anything, to change between jobs. So this base unit here, it could repeatably clamp on anything down to 5 microns. So that is 0.2 of a thousandth of an inch. You could be sure that that fixturing that you clamp on was going to be in the same place as the last time you clamped it. So where that's useful, maybe you need to switch over between jobs. Well, you can clamp a piece of fixturing you haven't used in months and be sure it's going to be in the exact same place you put it last time. Or let's say you're halfway through a job and something frantic comes up and you need to pull it off the machine. Well, you can do so reliably, and it'll be in the same place next time you put it in the system next time. And then everything else it's showing clamped in the system were the rest of our fixturing products that we don't really have time to get into, but some cool toys. Magnets, vices, clamps of all shapes and sizes. And again, it's always about selecting the best, not necessarily the best technology, but the best for the job at hand. So with that, we did some custom engineered fixturing solutions. This was kind of the fun stuff. So for really tough parts, really tough jobs, sometimes our catalog product didn't get it done. So like for instance, here was a job in Oklahoma where the challenge was to clamp basically parts that ranged from 6 feet to 14 feet long. It got machined from both sides. You needed lots of spindle access, so whatever clamped it had to be kind of low profile, which is usually the case. And it needed to be adjustable along this table. So this is what we settled on. Basically 8 vices across the table. Some were up on these horizontal faces that we call tombstones. And you can see here, like I said, coming at it from 2 sides with 2 different spindles. And normally we probably would have used milling magnets for this to hold that part down, but these were like hardened Inconels and hardened alloys that weren't really magnet friendly. Milling magnets is a whole deep subject I'd love to have time to talk about, but I don't want to take up too much of your time. Hopefully you have me on like 1.25 or 1.5 speed by now. So on the right here, this is like a pretty familiar site to the CNC metal cutting industry. So these chip bins fill up pretty quick. And the good news for any green thumbs out there, I mean, it looks like a lot of waste, but there's so much value in that metal. I mean, especially in cases where you know you're machining only aluminum all day, every day, aerospace grade aluminum. There's so much retained value that basically something like 95% of all metal chips get recycled. So they get sent back to material processing plants and forging houses to be resmelted down and recombined. In some advanced cases where shops are cutting so much metal, they actually bring that process in-house and have a closed-loop recycling where maybe the same chip or the same atom of aluminum might get cut multiple times a year in the same shop and reprocessed. It's super important also in the aerospace industry, where a part might be 95% weight reduced by the time you're done processing it. Speaking of that and material savings, back a little bit on that hybrid manufacturing we were talking about earlier. So these machines that can do both additive and subtractive manufacturing, a big benefit for them is reduced material waste. It's a cool video. I'll save the time for us right now. But basically, instead of starting like on the right here, normally you would start from a solid billet, so a solid hunk of metal, machining it down to your part. You can start from something that we call like a near net shape geometry, and traditionally this is done with like a forging or a casting, and then you machine it down to make it precise. But where additive pushes the envelope here is that there's geometries you can't really make a forging. Like it'd be very hard to make a forging or a casting in this shape of this turbine blade, but additive can do it. And believe it or not, even though this is an ugly looking part, once you machine it back down, you get something shiny like a traditional CNC part. So also down below shows kind of the reduction in metal chips by doing this. But one more cool use case for these hybrid machines is in like repair of super expensive parts. So a part like, wow, way back, a part like this, expensive turbine blades that go in both jet engines and like our gas turbine plants, for like natural gas generation plants. These are, like I said, like $100,000 parts, and if one breaks, you might be taking down a power plant that generates hundreds of thousands of dollars of revenue a day. So the ability to service these parts has never really been a capability. I mean, if a turbine blade breaks, you're just going to need a new one. But imagine only one of these fan blades breaking, and you have to scrap a $100,000 part. Well, now with these hybrid machines, you can come in and mill away, the broken part. You can add material back to create a rough geometry of that turbine blade, and then you can mill it back to form. So you have the ability to actually repair high-value parts with these additive machines or hybrid machines. So, like I said, never before seen capability. You're never going to be doing that for your house key. You'll probably just go get a new house key, but it kind of pushes the envelope of what's possible. We're almost there, but let's see. I just wanted to point out a few more examples of where this technology is used. It's in so much more than you might expect. Automotive and aerospace are big hitters, but even like consumer electronics, on two fronts. The semiconductor industry has a lot of need for CNC tooling, and that's maybe a key point, is that it's not always that the CNC parts are going into the end use product, like this Oculus Rift headset, for instance. While there's maybe no precision metal parts on the product itself, all of the injection molded tooling and a lot of the tooling to create these forms is probably precision CNC molds and stuff. And same with the semiconductor side. So it's a big industry that affects more than you might realize, and it's only growing. So the main point I wanted to show you with this was basically that these skills we've learned this week, not only are they transferable into a career, they're transferable into a pretty cool career and a cool growing industry. And I've got more to say, but I want to be respectful of your time, so please reach out if you want to know more. Tom can put us in contact. And thanks for listening, and thanks for this opportunity to reflect on my time. Just 3 years in the industry, but I know I'm going to be in manufacturing my whole life, so it makes for a fun career. Thanks.